Hello everyone, I am Hamed Javadi, a researcher with IMEC, and I am presenting the multi-target tracking pipeline that we developed for the FMCW radars based on the GMPHD filter. During my presentation, I will give a brief introduction to the PHD filter and also GMPHD filter. I will present the multi-target tracking pipeline that we developed for radars together with its evaluation results, and I will draw some conclusions at the end of my presentation. PHD filters are introduced in the context of random finite sets, or RFS. An RFS is a set of a random number of random states. In other words, we have a set of random states, and the number of these random states is also random. An RFS is completely specified by a multi-target density f of x. As you see here, we can define the probability of a subset X as the integral of this multi-target density. However, this multi-target density is a function of a set, and the integral of a function of sets is defined this way, which is pretty complex. Since an RFS includes a random number of random states, it fits very well in the multi-target tracking problems. But to have a solution based on RFS for multi-target tracking, we need a dynamic model and also a measurement model. The dynamic model is the the union of the set of the transition targets or states from the previous instance and the newborn targets. The set of the transitioned targets is also a union of a single target transition model. The measurement model is given by the union of the detected targets and also the clusters. In this framework, two probabilities, survival probability and detection probability, are included. The survival probability indicates the probability of staying state in the next step, in the next instance, and the detection probability shows the probability of a target being detected. Bayesian recursion based on these models is not tractable because of the high complexity of the probability densities, the posterior densities. However, Mahler, in his great paper, shows that instead of posteriors, we can propagate the probability hypothesis density or PHD functions. What is a PHD function? It's simply a function whose integral over a set X gives the expected number of elements in the region X. The number of elements of RFS within a subset X can be calculated with this relationship. And here, delta of X is the sum of all single state delta. If we denote the state, the location of each state by a delta function, delta of X becomes the sum of all of these deltas, and the number of states in a region X becomes the sum of the delta in that region. It is proved that PHD function equals to the expectation of these delta of X. There are several implementations of the PhD filter that attempt to make it tractable. The Gaussian mixture filter or GMPHD filter is based on these four assumptions: a Gaussian dynamic model, a Gaussian measurement model, state-dependent survival and detection probabilities, and it also assumes that the intensity or the PhD of the birth set is a Gaussian mixture. As you see here, a Gaussian mixture can be denoted by a set of means, covariance matrices, and also the weights. Each weight indicates the significance of its corresponding Gaussian component. And this is the flowchart or the pipeline of the GMPHD filter. It resembles a conventional multi-target tracking algorithm. It includes initialization, prediction, update, pruning, merging steps. In the pruning and merging, the exploding number of the Gaussian components is avoided. In initialization, the Gaussian components are initialized based on some initial observation data, and each component is assigned to with a unique tag. So T here is the set of the tags. Each tag is uniquely assigned to a Gaussian component. I am not going through the whole mathematics here. However, I want to highlight the importance of the weights in the GMPHD filter. The weights are updated based on mainly two quantities. One is Q. Q is the likelihood of any measurement to a predicted measurement based on some given state, of course, some predicted state. And kappa here is the clutter model. And these weights specify the significance of the Gaussian components. And the strongest components are considered as the set of the targets given by the filter. So only the states with weights which are higher than a threshold is considered as the set of the states in that instance. But other states still remain in the loop. This is the pipeline that we developed for radar data. Radar cube goes through a static targets removal where the zero Doppler data is removed. Then by applying a 3D Fourier transform, we obtain the beans, the data, the observation data of the radar in different range, azimuth, and Doppler values. Then CIFAR gives the detected beams in different ranges, velocities, and azimuth beams. This is an example of the CIFAR output. As you see here, we have two targets in different ranges, and these two set of points are obtained for these scenario. And then by applying dbScan, clustering happens. And here clustering gives three clusters. One of them is obviously a clutter, which is due to perhaps some multipath from the floor. We use dbScan for clustering. dbScan itself filters many clutter data. However, the clutter due to multipath still remains in some observation data. The mostly common uniform model here doesn't fit the observation data that we have. Instead, we suggest to use the clutter model, which depends on the weights, because as I said, the multipath clutter, the clutter which we have is mainly due to multipath, and multipath depends on the states. And with this W, we keep the dependency of the clutter on the states. Lambda of C is the rate of the clutters that we see in the observation data, in some sample data, and A is the area of the radar's field of view. We also apply another modification to the GMPHD measurements. Each observation data is conventionally considered as the centroid of each cluster, but this may be inaccurate. Instead, we suggest to go with a more appropriate cluster points instead of just the cluster centroid. To this end, we create an association matrix. The rows of this matrix are the likelihood of the measurements given the predicted measurements. Here, for example, in this example, we have 4 measurements, 4 observation data, and 2 predicted measurements. So there will be at most 2 candidates per cluster, and among these 2 candidates, the one which gives the highest likelihood is chosen as the representative of the cluster. And here some results of the algorithm evaluation. Firstly, we evaluate the algorithm by simulated data. The simulation scenario includes 8 targets with different locations and movements. Here you see the tracking results. Here what's important is the stability of the color. The color of the track shouldn't change. And here we compare the performance of our developed PhD filter with a conventional JPDAF filter. As you see, we compare it in terms of Hausdorff distance, so the lower the performance is better. And you see here that we get a better performance for the PhD filter. These are some experimental results. The dots are the radar-based results, which are mapped over the video frames. Different scenarios are shown here. The dots should track the feet location. In the last scenario here, the dots track the hip. conclusion, the GMPHD filter has no data association and hence it's pretty light, best for edge devices. And also we found that the modification of the radar's observation data using the bonding boxes improves the filter performance. As remark, there are two major drawbacks with GMPHD. First, the high sensitivity to the clutter model, and the second one is the hard selection, which is used for selection of the states. CPHD alleviates these drawbacks in cost of how much higher complexity. For your attention.